Okay, let's start the last section of the ZAERO Advanced Training, Section 11, Nonlinear Flutter Analysis. So first we'll go over the formulation of the nonlinear flutter module in ZAERO. This module computes the time domain responses of an aeroelastic system that contains either the structural nonlinearity or a nonlinear control system. So we do that by defining a nonlinear aeroelastic system as a function of multiple nonlinear parameters, Vi, where I is 1 through n, governed by these equations. So you can see that our mass, damping, and stiffness matrices are all functions of these nonlinear parameters, and then our aerodynamics are also a function of these aerodynamic parameters. Any response of the system can be defined as the nonlinear parameters such as grid point displacement or accelerations, element forces, component loads, sensor outputs, actuator inputs, etc. Now this equation, you can see that we have n number of nonlinear parameters. However, in ZAERO, you can only have up to 2 nonlinear parameters. So next, the nonlinear flutter module generates the state space equations at m discrete values, the Vij. So this represents the 2 different nonlinear parameters. So the first nonlinear parameter, we have n discrete values, and for the second nonlinear parameter j, we have m discrete values. So we now have our x dot equals ax plus bu. A is we have I times j number of matrices, or sorry, n times n number of matrices. So this is the ij matrix, and then this is the bij matrix. So from the continuous time domain, we convert that to the discrete time domain. So now we have x at time step k plus 1 is a bar ij times xk plus b bar ij times uk. We also introduced the initial condition and external disturbances u0 to start the time marching computations, and at each time step we compute the nonlinear parameters v and interpolate a bar and b bar for the next time step. So this is the solution procedure in the nonlinear flutter module. In our input, we have the KHH, IJ, MHH, IJ, BHH, IJ, and QHH, IJ for each Vij, where I ranges from 1 to m and j ranges from 1 to m. We then compute the a bar and b bar ij. So these are in the discrete time, and then we store the a bar ij and b bar ij on the runtime database. This step is done before the time marching simulation begins. Then for the time integration computation, we start at the initial condition, which includes the trim condition and Cassie not. We set the time to 0 and our time step to 1. So this is the first time step. We then compute the Vi of Cassie. So for the first time step, the Vi will just be 1 and 2. Like I said in ZAERO, we have 2 nonlinear parameters. So we compute those 2 nonlinear parameters. We then interpolate a bar and b bar based on our computed V. Now that with the computed a bar and b bar, we can compute our states at the next time step. So xk plus 1 is a bar times x of k plus b bar uk. We then increment t by delta t the time step and increment k by 1. We move to the next time step and move back and compute our nonlinear parameters again for the next time step and go through. Meanwhile, at every time step, we output the transient response based on our states x. So as an example of what you can do with the nonlinear flutter module, we can have an actuator with Freeplay, where the without Freeplay, of course, the torque theta diagram would just be a straight line, but with Freeplay, within the Freeplay region here, theta, our torque is 0, and then outside the Freeplay region, then we have the torque force. So with this example, we have 3 sublinear regions. So these are the bulk data cards. We have the nonlinear flutter and the nonlinear system matrix cards. The nonlinear flutter card defines the data needed to perform the nonlinear flutter analysis, and it's referred to by the case control section, the nonlinear flutter case control command. The nonlinear system matrix bulk data card defines the matrices of the air elastic system for the nonlinear open or closed loop flutter analysis. So the nonlinear flutter card optionally refers to an ASE controller card for closed loop systems. Optionally refers to the MLD stat card to define airframe states. It's required to refer to the MLD command and or a dgust card to define the external excitations. It's required to refer to the MLD time card, which defines the time parameters, and then optionally can refer to the MLD print, although it is highly recommended to refer to an MLD print so that you can see what the responses are. The minstat card is required. This defines parameters for the rational function approximation. Obviously, being a nonlinear analysis, a frequency domain analysis is not available. And then the nonlinear flutter card refers to the flutter bulk data card to define the air elastic system. Lastly, the nonlinear flutter card refers to the nonlinear system matrix cards. These define the matrices of the air elastic system at a given value of nonlinear parameters. So this is the nonlinear flutter bulk data card. It's split up into 3 different sections here. The first row, much like the M loads, E loads, and G loads cards, refer to our ASE controller, flutter, minstat, MLD stat, MLD command, MLD time, and MLD print. So that operates the same as the other cards. Next, we have 2 rows which define the nonlinear parameters. So the first row is the first nonlinear parameter, and the second row is the second nonlinear parameter. You optionally can have only one nonlinear parameter. So this row, you would make use of the first row. The second row, basically you would leave it blank. So we have a label. We define the nonlinear parameter through 2 label and I key values here. So this label and I key operate very similar to the MLD print card, where you have a label and I key to define the parameter. And then we have 2 of these so that you can easily, oftentimes you need 2 parameters to define the nonlinear parameter. So for example, in the case of Freeplay, you could take 2 grid rotation values and subtract them from each other to come up with the relative grid rotation of one grid point relative to a second grid point. That could be your Freeplay nonlinear parameter. So in that case, CA1 here is a factor, so CA1 would be positive 1, CA2 would be negative 1. That allows you to subtract the grid point rotation of the second grid from the first grid. The second nonlinear parameter is the same thing. We have a label and I key, and then a factor, and then a label, I key, and a second factor. Lastly, we have the init A and init B. These define the initial value of the nonlinear parameter at time 0. And then lastly, we have the third section, which defines a table of nonlinear system matrices. So our first nonlinear parameter, we can split that up into as many discrete values as we would like. This is an open-ended input. The second nonlinear parameter, you can only have up to 7 discrete values. And then this is our table of nonlinear system matrices. So what ZAERO does is at each time step, it calculates the nonlinear parameter and then does this table lookup. So if we move down to this example here, this table here, the first nonlinear parameter, we have discrete points at -20, 0, and 40. The second nonlinear parameter, we have -100, 0, 0, and 100. So during simulation, if our first nonlinear parameter is -10, our second nonlinear parameter is -100, we will now interpolate on this table. So -10 is between -20 and 0. So ZAERO and the second nonlinear parameter is exactly minus 100. So ZAERO will take these two system matrices, this 10 and 101. These refer to the system matrices that we'll look at in a minute. Take the A bar and B bar matrices from these two, and then because minus 10 is between minus 20 and 0, we'll interpolate between the A bar matrix from the 10 and the A bar matrix from the 101 to give the final A bar and B bar matrix for that particular time step. Similarly, if our first nonlinear parameter is minus 10, our second nonlinear parameter is minus 50, it would interpolate among all four of these A bar and B bar matrices. Now note here we have repeated values of 0, so when the nonlinear parameter is exactly 0, it will choose one of these, and I forget which one it is, if it's the first one or the second one. That is in the nonlinear Flutter bulk data card as to which plant it will choose. So the first nonlinear parameter VA is defined as CA1 times FA1 plus CA2 is FA2, where the FA1 and FA2 are defined by the label and I-key entries. And then the IDIJ, that's these parameters here, refer to the nonlinear system matrix bulk data cards to define the sublinear aeroelastic system. This is a list of the label and I-key values, so it is very similar to the MLD print card. We can measure grid displacement, grid rate, and grid acceleration. We can also measure generalized modal coordinates, the first and second time derivatives of the modal coordinates. We can measure force at a particular grid, moment force at a grid. We can measure a load mod card, so we can measure component loads. We have the DMI option for arbitrary modal values. We have the EXT out. The EXT out can be very useful because then you can build up some sort of measurement using your control system definition and then feed a signal out using the EXT out. This is the nonlinear system matrix bulk data card. So this defines the system matrices of a sublinear aeroelastic system. So we have our mass, damping, and stiffness matrices are defined here. So that the mass matrix, this is a matrix name, refers to our mass matrix. Then we have our damping and stiffness matrices. Each of the mass, damping, and stiffness matrices have a coefficient. So if you need to multiply those by some generic coefficient, you can do that here. Let's move back to the first row here. So our delta Q, coefficient Q, and gen Q, that's these three fields here, define the modified aerodynamics. If the coefficient Q is real, it's a multiplication factor to the matrix defined by the gen Q entry. And if it's an integer, it refers to the identification number of a MinStat card. Next, for the con force and for a control surface with a Freeplay angle plus or minus theta naught, there are three sublinear aeroelastic systems given here. So we have this constant force that we need to introduce, and that constant force is given here. So the con force here is this total constant force. The reason that's needed, if we come down here to our Freeplay diagram, you can see that our torque theta diagram out here needs to be shifted down, and then out here needs to be shifted up. And then we do that shifting through the force here, this constant force. So our Kf and K naught are the generalized stiffness matrices associated with the absolute value of theta is greater than theta naught, and then the K0 is when theta is within the Freeplay region. The constant forces in this case are represented by the offset moment, phi transpose times Kf times theta naught, where Kf is the physical stiffness matrix without Freeplay. Now, without the constant force, the resulting torque theta diagram would have a discontinuity. We would have this line, and then this straight line, and then this line, and that would be incorrect. So once again, with the Freeplay, you have to have this constant force to create this piecewise continuous torque theta curve. The G-set mat here is a flag to specify whether these matrices are defined in the G-set or the H-set. And then the delta mat is a flag to indicate whether or not these mass damping and stiffness matrices are delta increments or the actual mass damping and stiffness matrices. So let's go through several test cases here. First, we have a validation case, a 3 degree of freedom airfoil with Freeplay. The airfoil section is an incompressible flow with plunge, pitch, and flap rotation degrees of freedom. The nominal angular gap delta is plus or minus 2.12 degrees, is introduced in the flap rotation degree of freedom, which defines the Freeplay. Both the experimental and analytical results are obtained by Tang et al. At speeds ranging from 4.3 meters per second to 24 meters per second. And this is high quality test measurements, and they also provide accurate structural data. And this is considered as a standard benchmark case for validating the nonlinear aeroelastic methodology. So this is our diagram of the airfoil that they've tested, and then this is the torque theta diagram for the flap displacement beta. These are the equations of motion. So we have SMHH times C double dot plus SCHH times C dot plus SKHH times C plus this lambda parameter times M beta, and then minus Q infinity times Q times C. These are the aerodynamics equals M naught. So MHH and CHH are the generalized mass and damping matrices. KHH is defined by KH, K alpha, and K beta. This is the generalized stiffness matrix without Freeplay. Now note here that our generalized coordinates are actually equal to our physical coordinates. So C is equal to minus H, alpha, and beta. These are the generalized coordinates, and that's why in our KHH matrix we have these simple terms, just KH, K alpha, and K beta. So minus H is the plunge mode, where positive is upward, alpha is the pitch mode, and beta is the flap mode, and is the relative deflection angle between the airfoil and the control surface. Q infinity times Q is the time domain generalized aerodynamic force matrix. Now, in order to compute the 2D aerodynamics from the 3D model, in ZAERO we've defined a high aspect ratio rectangular wing, which is modeled by a single ZAERO7 bulk data card, but the unsteady pressure is then zeroed along all strips on this 3D wing except the root strip using the CP-FACT bulk data card. So we have this very high aspect ratio ZAERO7 half-span model, and then using CP-FACT we zero out the CP on all of the boxes except this the innermost strip. So what that does is when we solve the aerodynamics in the 3D, we are approximating the 2D aerodynamics because these boxes are seeing the influence of this very high aspect ratio wing. So the aerodynamics at this innermost strip are approximately equal to the 2D aerodynamics. And we have to do this because ZAERO does not have the 2D aerodynamic solver. It is 3D only. Now the vector lambda times m beta, that's right here, in the equation represents the nonlinear structural effects due to Freeplay. So lambda is equal to -1 when beta is outside the Freeplay region, and lambda is equal to 0, or sorry, lambda is -1 when beta is inside the Freeplay region, and lambda is equal to 0 when beta is outside the Freeplay region. So this is a switching parameter for the Freeplay nonlinearity. M beta here is 0, 0, K beta times beta plus this M naught. M naught is m bar naught. So this m bar naught is equal to k beta times delta naught when beta is greater than 0, and minus k beta times delta naught when beta is less than 0. This is the offset moment, so that we get the piecewise continuous torque theta diagram. So we can see, I think we'll see that on the next slide. Yes. What we'll see on the next slide is that this lambda parameter introduces Freeplay by subtracting out this k beta, essentially from SKHH. So in effect, this, when we are inside the Freeplay region, our KHH matrix, this will turn into a 0, which gives us 0 stiffness. This is as the freeform FEM solution file that's imported into ZAERO by the assign FEM. So this gives us the mass damping and stiffness matrices and then the eigenvectors. So this is our plunge mode, this is our pitch mode, and this is our flat mode. So for the plunge mode, our two grids both deflect in the z direction by -1. For our pitch mode, both grids are rotated about the y-axis, and then the second grid also deflects down, so that we have the pitch mode. And then for the flat mode, the first grid remains stationary, and the second grid simply rotates about the y-axis. Next, we'll look at the nonlinear parameters in the nonlinear system matrix bulk data cards. So we need to define the flap rotation angle beta as the nonlinear parameter, where beta is the difference between the rotation degree of freedom, R2, about the y-axis at grid points 1 and 2. That is, beta equals rotation about the y-axis at grid 2 minus rotation about y-axis at grid 1. And then the nonlinear domain can be divided into 3 linear subregions and represented by 3 locally linear systems with respect to the nonlinear parameter beta. So region 1 is when beta is less than minus 2.12 degrees. Region 2 is when beta is within plus or minus 2.12 degrees. And region 3 is when beta is greater than 2.12 degrees. And now we have 3 nonlinear system matrix bulk data cards to define these 3 locally linear systems. So for region 3, we have our offset moment. For region 2, we do not have an offset moment, but we subtract out the the flap hinge stiffness here, so that we have 0 stiffness on the flap. And then for region 1, we have our offset moment. K hinge is 0, 0, K beta for the stiffness of the hinge. K delta M is 0, 0, and then minus K beta times delta naught for the negative offset moment. K delta P is the positive offset moment. And then P naught is the external disturbance due to a 1-cycle flap oscillation. So that will be our external disturbance to excite the system. The 3 nonlinear system matrix bulk data cards are shown here. So for nonlinear system matrix ID 100, that's region 3. You can see we have the K delta P offset matrix here. For 101, that's region 1, we have the K delta M offset moment. And then for nonlinear system matrix ID 111, we're subtracting out the K hinge here. Now, ideally, you would think the factor to K hinge should be -1. However, to avoid a non-positive definite matrix, instead of subtracting all of K hinge and due to numerical noise, we're just subtracting off 0.999999 times K hinge. This will ensure that we have a positive definite stiffness matrix, but the remaining stiffness is so small that it will not affect the analysis. These are the bulk data card interrelationship diagram, and then the nonlinear flutter card. So the nonlinear flutter card, we have an ID of 1. refers to the flutter card with ID 101. We have the MLD command is the external disturbance. So the 33 refers to MLD command. And then we have our MLD time and MLD print. Our nonlinear parameter is made up, as we said, of the relative grid rotation. So we have ID grid 2, the rotation, the y rotation about grid 2, the factor is positive 1. So it's this value. This factor is -1. So this grid rotation minus the y rotation at grid 1. That's our nonlinear parameter. Now we split our region, our nonlinear parameter, into 3 sublinear regions. So between -100 and -0.037, this is in radians, so that's that 2.12 degrees. We refer to our nonlinear system matrix 101. So between, when we're in this region, we'll interpolate between system matrix 101 and 101. So when you interpolate 2 of the same thing, you just get back the 101. So that ensures that in this region we have a constant system matrix. Now we do our switch so that between 2.12 degrees, plus and minus 2.12 degrees, we have nonlinear system matrix 111, which is the Freeplay stiffness matrix. And then greater than 2.12 degrees, we have the nonlinear system matrix ID 100. So that will give us our resulting torque theta diagram as shown here. So next we'll look at the results. So we have plotted the root mean square of the pitch, plunge, and flap rotation at various speeds. And the ZAERO results correlate well with the analytical results. And the transition of the nonlinear responses from low speed to high speed show 5 types of motions. First, we have damped decay, which is this region. Then we have periodic LCO, which is this region and this region. Next, we have intermittent chaos, which is this region here. Then we have nearly harmonic LCO, which is this region and this region. And then we have flutter, which is out here, which there are no results to plot because the RMS will just goes to infinity because it's flutter. So all 5 types of motion are observed in both the analytical and experimental results. So the ZAERO results are given by the black squares connected by a line, and then our experimental results are given by the symbols. So we have a diamond, open diamond, a triangle, and a circle. So the black circle, where the gap is plus or minus 2.12 degrees, that's what we've simulated in ZAERO. So you can see that all 3 regions and the transition points between the regions, we've matched pretty well between ZAERO and the experimental data. It's interesting to note here, when we go from the periodic LCO and then we go through the intermittent chaos and then the nearly harmonic LCO, the frequency, the dominant frequency changes. And we've matched that pretty well with ZAERO. And here are some time domain plots. So the periodic LCO is obtained only if the amplitude of the flap oscillation is sufficiently large. So this is our angle of attack, this is our beta, our flap angle, and then our plunge. So you can see we've matched the experimental data is the dashed line, and then ZAERO is the solid line. So with alpha and beta, we've done a pretty good job matching that. With the plunge, ZAERO overpredicts the plunge amplitude by a little bit. The intermittent chaos, we've named it that because you can see the alpha and beta is kind of looks like this, and we've also matched that pretty well. And then finally, the nearly harmonic LCO is a higher frequency. So our angle of attack, our flap rotation angle, and then our plunge. You can see that the plunge amplitude is much smaller as compared to the intermittent chaos in the periodic LCO. So we'll continue looking at some more sample case studies. Next is the flight loads effects on Freeplay induced limit cycle oscillation of the F-16 horizontal tail. So our background here, control surface Freeplay could induce limit cycle oscillation, LCO, that could have the following effects: structural fatigue, pilot handling and ride quality, confine the maneuver envelope, the weapon aiming of military aircraft, and also induce flutter. So to avoid these issues, the mil-spec confines the Freeplay limit to within plus or minus 0.017 degrees, which sets a goal of no Freeplay-induced vibration during normal operation of the airplane. This plus or minus 0.017 degree allowable Freeplay limit is a stringent requirement that increases manufacturing costs and increases maintenance costs because this is a very small Freeplay value. It's very tight tolerance. Now, however, an F-16 horizontal tail was observed having 6 times the mil-spec limit, but no LCO occurred during the flight. So this leads to the following questions. Is the current Freeplay mil-spec too strict? And is LCO not observed due to the horizontal tail always being loaded during the flight? So we will use the ZAERO Nonlinear Flutter module to investigate these questions. The objective here is to perform a nonlinear flutter analysis for the F-16 with horizontal tail Freeplay to study its LCO characteristics. We're going to look at various Freeplay limits under various maneuver conditions subjected to various external excitation due to both pilot input and gust loads. And we're going to also do this without rigid body modes, which is a restrained structure which would simulate a wind tunnel test, and with rigid body modes, which is an unrestrained structure which would simulate an F-16 in flight. The ZAERO Nonlinear Flutter module is employed for this study. And as we said, the Nonlinear Flutter module has been validated with wind tunnel measurements, as we saw in the last section. The Nonlinear Flutter module has been adopted by industry for the study of Freeplay-induced LCO. And the Nonlinear Flutter module adopts a direct simulation for the transient response of a nonlinear aeroelastic system subjected to various external excitations. So this is the structure and aerodynamic modeling of the F-16. The flight condition is fixed at Mach 0.8, but we'll do the simulation at various altitudes. We have 2 sets of stiffness matrices computed by MSc Nastran. K normal for the linear nominal structures, and K free for the linear free horizontal tail structure, which has 0 stiffness of the horizontal tail actuator. Additionally, we've added a 200-pound balance weight to the nose of the F-16 for static stability because we've not reproduced the F-16 flight control system here. Now, the major technical issues are how to generate one set of structural modes, generalized coordinates to represent the deformation both within and without Freeplay, and then how to generate the trim loads with the horizontal tail Freeplay using the ZAERO linear trim analysis. So our structure model is shown on the left here. We have a detailed wing and horizontal tail, and then our fuselage you can see is a simple beam. The aerodynamic model is shown on the right. The body is made up of 264 panels. The strake has 103 panels. The wing is 663 panels. The vertical tail is 450 panels. The horizontal tail is 102 panels. And the ventral fin is 34 panels. Now we're going to use the fictitious mass mode method to generate our modes. So the objective of the fictitious mass method is to generate one set of modes that contain both the free horizontal tail modes within Freeplay and the elastic modes without Freeplay. The fictitious mass modes, phi-fm, are generated by adding a large mass moment of inertia, delta m fm, to the nominal structure. So when we do that, as shown here, we generate these modes. We've excluded modes 1 through 3. Those are the rigid body modes. Now mode 4 is a horizontal tail, nearly rigid body torsion mode. So there's very little elastic deformation in the horizontal tail here, and you can see that it looks like just a horizontal tail rigid body torsion mode. So next, mode 5, this is our first true elastic mode. So this is a fuselage and wing bending mode. Mode 6 is our wing bending mode. Mode 7 is our fuselage and horizontal tail bending mode. Mode 8 is the horizontal tail bending mode. And then if we jump all the way up to mode 18, this is our elastic horizontal tail torsion mode. Now we want to continue to look at the fictitious mass method here. The generalized mass and stiffness, m bar normal and k bar free of the free horizontal tail structures are given by these equations. So our Cassie, we've taken the fictitious mass mode shapes, and we can solve for m bar normal and k bar free. So m bar normal is the phi fm times m normal times phi fm. K bar free is phi fm transpose times k free times phi fm. And then for the nominal structure, the generalized mass and stiffness, our mass is the same, but our stiffness now, we take the stiffness matrix from the nominal model to get k bar normal. Now the natural frequencies of the free horizontal tail structures and the nominal structures with the fictitious mass modes agree very well with those of the direct modal analysis. So the point of this table is to validate that the fictitious mass method gives us back the same natural frequencies as the direct method. So with the nominal structure, the first 3 modes are the rigid body modes, and now you can see modes 4 through 10, we match the natural frequencies very well. And now with the free structure, the direct method will get 4 rigid body modes, because remember the last rigid body mode is the horizontal tail rigid body motion. And then the remaining modes, elastic modes, are seen here. Also, you can see that the natural frequencies of the nominal structure and free structure correlate decently well. Next, we're going to perform a flutter analysis to further validate the fictitious mass mode shapes. So for the nominal structure, our natural modes are given by this equation, which leads to the flutter equation shown here. And for the free structure, the natural modes are given here with this flutter equation. So the free structure, of course, we use the free stiffness matrix. For the nominal structure, we use the nominal stiffness matrix. The fictitious mass approach is more straight or more similar between the two. We use the fictitious mass mode shapes for both, but we only substitute out the stiffness matrix. Whereas in the direct, we use the modes associated with the free and the nominal structure. So we'll look at the flutter results. The linear flutter analysis results indicate that the fictitious mass modes can represent both the nominal and the free structures. So the direct method with the nominal structure, this is the VG diagram, and we have no flutter. Using the fictitious mass modes, this is our resulting VG diagram, and we also have no flutter. If we pick out some of the modes, you can see that the characteristics are fairly similar. Now if we move to the free structure, the direct method gives us some instability here at 800 feet per second, and then a second instability out here. Using the fictitious mass modes, our flutter velocity is 815 feet per second as compared to 800, and our flutter frequency is 10.59 versus 10.60. So the frequency is very similar. Also, you can see that our second instability is also captured decently well. So this means that we can use the one set of mode shapes to represent both structures, which is needed because in the nonlinear flutter module, we have to stay with the same consistent set of modes. We can't switch modal basis in the middle of the time simulation. So next we'll build up the nonlinear system. So we have 50 modes used for the Freeplay induced LCO analysis, and the nonlinear equations of motions are formulated here. So within the Freeplay region, we have the Freeplay stiffness matrix with no offset moment. Outside the Freeplay region, we have the nominal stiffness matrix, and then we have our offset moments. FG here is the external loads, which include the trim loads, maneuver loads, and gust loads. Our phi FM times k nominal times theta 1 and phi FM times k nominal times theta 2 are the offset moments. And so this is the resulting torque theta diagram. So next we'll do a trim analysis. The trim analysis solves the trim solution at a given angle of attack, or NZ. The trimmed angle of attack, horizontal tail deflection angle, and the modal displacement are used as the initial condition of the transient LCO analysis. And before external excitation starts, no oscillation should occur, and the transient response remains at the steady state trim solution. Now, because the horizontal tail is loaded due to trim, the trimmed horizontal tail deflection angle must be outside the Freeplay limit. And because an infinitesimal trim load is sufficient to push the horizontal tail to the boundary of the Freeplay limit, the horizontal tail hinge deformation is in the nominal structural range due to the remaining trim loads. Thus, a linear trim analysis using the nominal structure is valid. And this is going to shift the Freeplay limit to plus or minus theta naught to in between 0 and 2 times theta naught in the LCO analysis. And the hinge moment of the horizontal tail due to the trim loads is used to identify the flight loads effects on LCO. And we'll have two scenarios here for the LCO analysis. The first is the restrained structure without rigid body modes to simulate a sting-supported wind tunnel flutter model at NZ equals 0 Gs, where the horizontal tail is nearly unloaded. This is subjected to a 1 minus cosine gust with a 20 foot per second gust velocity. And then secondly, at an angle of attack not equal to 0, where the horizontal tail is loaded, subjected to a pilot command to the horizontal tail. And then an RMS of the leading edge tip displacement subjected to a 50 foot per second gust with various AOA and Freeplay limits. Next, we have the unrestrained structures with rigid body modes to simulate the free flight conditions. At 1G trim, subjected to a 50 foot per second gust with various Freeplay limits, and maneuvering due to a pilot command at a Freeplay limit of plus or minus 0.1 degrees. So first we have the restrained structure at NZ equals 0 Gs subjected to gust. The 1 minus cosine gust has a gust velocity of 20 feet per second, as shown by this figure. The LCO occurs at Mach 0.8 and sea level as long as the Freeplay exists. The maximum horizontal tail rotation angle is approximately twice that of the Freeplay limit, and if under the unloaded condition, the LCO is unavoidable, regardless of the mil-spec limits. So if we start out at plus or minus 1 degree Freeplay, you can see the rotation angle is between plus or minus 2 degrees. When we reduce the Freeplay to plus or minus 0.1 degrees, our rotation angle is plus or minus 0.2 degrees. And when we reduce the Freeplay to plus or minus 0.017 degrees, which remember is the mil-spec, we still have a response of approximately plus or minus 0.034 degrees of Freeplay. So we still get the LCO because the horizontal tail is completely unloaded. Next, we have a restrained structure at an NZ of 0 Gs subjected to gust. So the leading edge tip displacement at Mach 0.8, 20 feet per second, and sea level. So with a 1 degree of, restrained structure. This is the leading edge tip displacement, whereas the last figure was the rotation angle. So our leading edge tip displacement, you can see with 1 degree free play, we get a large response. When we cut that down by an order of magnitude, we cut our response down by an order of magnitude, and then at 0. So next we have a video here of what the response looks like when it's when we use the pilot command to initiate the excitation. So this is at Mach 0.8, sea level, angle of attack is 1.4 degrees, and our free play is plus or minus 0.2 degrees. And the LCO here disappears after the excitation from the pilot input command vanishes. So in this video, we've amplified the deformation by a factor of 10. So you can see that with our input command, the pilot gives these doublets, and then this is the resulting rotation angle in the tail. So you can see that as we go through these regions where the tail is unloaded, we have an LCO response of the tail. And then when the pilot loads the tail due to these commands, the LCO actually disappears. And now what we've done is plotted the response due to various angles of attack and free play. So the root mean square value of the leading edge tip displacement at Mach 0.8 and sea level subjected to a 50 foot per second gust is plotted. Now the RMS value increases as free play increases as expected. So if we look at the free play axis, as we increase free play, then the RMS of the response increases. Next, the LCO vanishes when the angle of attack or the torque increases, suggesting that the LCO may not occur if the horizontal tail is loaded during trimmed or maneuvering flight. So as our angle of attack increases, the RMS of the response decreases. And when we increase the angle of attack enough, we can actually make the response completely disappear. So we'll look in more detail here. Both the upward and downward gust with a gust velocity of 50 feet per second are analyzed, and the more critical case is the downward gust. Now, under a given angle of attack, an increase of free play angle can induce LCO. So if we start out at this condition where the LCO disappears, we have our free play angle of plus or minus 0.8 degrees, and the angle of attack is 0.8 degrees. Now, if we increase the free play angle to plus or minus 0.1 degrees, we now have LCO occurring. So by increasing the free play angle, we've now allowed LCO to develop. But now, under a given free play limit, increasing the angle of attack can now eliminate the LCO. So increasing the angle of attack actually increases the load on the tail. So we keep the free play the same at plus or minus 0.1 degrees. We increase the angle of attack to 1 degree, and you can see after the excitation, the LCO disappears. Next, we'll look at the unrestrained structure at a 1G trim subjected to gust. So this is, once again, at Mach 0.8, sea level, subjected to a 50 foot per second gust. Our trim solution is an angle of attack of 1.26 degrees. Horizontal tail deflection angle is minus 0.96 degrees, where the torque is minus 976 inch-pounds. And no LCO occurs, even with a free play limit up to plus or minus 1 degree. So at this particular loading condition, no matter how large we increase the free play up to 1 degree, we have no LCO developing. Next, we'll excite the system with a pilot command. So we have Mach 0.8, altitude of 10,000 feet, 1G trim condition, and the free play limit is plus or minus 0.1 degrees. Now LCO occurs during the short period when the horizontal tail is unloaded, but then disappears after the pilot command finishes and the horizontal tail is loaded once again. And the LCO disappears even if the pilot intentionally unloads the horizontal tail, because the aircraft is untrimmed and the horizontal tail will be rapidly loaded again. So this is our input command. So you can see that as we transition through these regions where the horizontal tail becomes unloaded, we develop an LCO response. After the pilot stops yanking the stick back and forth, the LCO disappears. And even in these short time periods where the horizontal tail becomes loaded, you can see the LCO quickly disappears. Continuing, this is the same as the last slide, but now we've increased the Freeplay limit to plus or minus 1 degree. Once again, the LCO disappears after the pilot command finishes. And this raises the question, does this mean that the Freeplay has little impact on LCO for free aircraft under trim and maneuver loads? So once again, as we're maneuvering, the tail becomes unloaded, LCO quickly develops, but then when the tail is loaded again, the LCO disappears. This is even at plus or minus 1 degree Freeplay. Now we'll want to compare the responses between the Freeplay structures and the nominal structures. So at Mach 0.8, sea level 1G trim, Freeplay limit of plus or minus 0.1 degrees. The responses of the two structures are similar, except the LCO occurs in the period of the pilot command for the Freeplay structure, and we have a different resulting angle of attack after the pilot command input. So on the top, we have the Freeplay structure. On the bottom, we have the nominal structure. So this suggests that a horizontal tail Freeplay limit of plus or minus 0.1 degrees has a small impact on the overall performance of the aircraft. So you can see the resulting angle of attack here ends up being different between the nominal structure and the Freeplay structure. And the rotation angle of the tail, from these two plots, you can clearly see the Freeplay developing. So the conclusions here from this case study is for a restrained F-16 structure at NZ equals 0, the horizontal tail Freeplay could induce LCO even with a very small Freeplay as expected. However, the LCO disappears when the horizontal tail is loaded. Now for an unrestrained F-16 structure, even with a large Freeplay angle, LCO occurs only within a short period of time when the horizontal tail is unloaded. When the horizontal tail is unloaded, a transient maneuver will be developed, and then the horizontal tail is rapidly loaded again, because it's very hard to keep the aircraft in a condition where the horizontal tail is unloaded. And it's unlikely that an F-16 can maintain an unloaded horizontal tail for a sufficiently long time until the LCO is fully developed. Now, however, this same conclusion cannot be made for the rudder since it is normally unloaded. Now, for other aircraft, the above conclusion may not hold, and it requires verification by the nonlinear analysis. And additionally, wind tunnel tests followed by a flight test is recommended to verify the analysis. For our next sample case study, we'll look at the folding wing with the bilinear stiffness in the hinges. So in this case, we have a folding wing which has a capability of changing its external shape substantially by folding the wing along two hinge lines. One is along 20% span and the other is at 52% span. And because of the hinged structure, the stiffness that connects the wing root to the fuselage and the outboard wing section to the inboard wing section could be bilinear due to backlash. That is, the stiffness within a small angle of the bending degree of freedom is much lower than that of the nominal structure. This bilinear structural characteristic could induce aeroelastic problems such as limit cycle oscillation. And the purpose of this test case is to demonstrate how to perform a nonlinear flutter analysis using the nonlinear flutter module for the folding wing with bilinear stiffness structures. So this is the upper and lower skin modeling, and this is the spar and rib modeling of the structure. So you can see this is the inboard hinge and this is the outboard hinge. Now the hinge line that connects grid point 5001 and 5002 is modeled using a CLS2 that specifies a torsion spring about the hinge line to simulate the actuator stiffness. And then a similar concept is applied to the outboard wing section between grid points 5003 and 5004. So this is our structure model, and then this is the aerodynamic model. So we have the fuselage, we have the inboard wing, and the outboard wing. Next, we need to model the bilinear stiffness of the hinge lines. So theta in and theta out are the torsional deformation about the inboard and outboard hinges, respectively. So theta in is the rotation 1 degree of freedom of grid point 5001 minus rotation 1 degree of freedom of grid point 5002. Theta out is the rotation 1 degree of freedom of grid point 5003 minus the rotation 1 degree of freedom of grid point 5004. The bilinear stiffness is introduced in the CLASs as shown here. So for the inboard hinge, inside this region, we have a soft spring where the spring stiffness is 10 to the 5 foot-pounds per radian. And then outside the soft region, the hinge stiffness is 10 to the 7 foot-pounds per radian. And then our outboard hinge follows the same definition. So if we look at the resulting torque theta diagrams, they're shown here. So the slope here is 10 to the 5 foot-pounds per radian, and then this slope is 10 to the 7 foot-pounds per radian. Now we have 4 sublinear stiffness matrices. The nonlinear stiffness characteristics of the folding wing can be divided into 4 sublinear domains, and each subdomain can be modeled by a linear structural model. So this gives 4 structure models, and each structural model generates a stiffness matrix using Nastran. Our first case is the nominal stiffness matrix, where both rotation angles are outside the soft spring region. So k theta is 10 to the 7 foot-pounds per radian. If we jump down to this last one here, in out dot kgg, this is where both springs are inside the soft region. So k theta is 10 to the 5 foot-pounds per radian. Then we have kggo. This is where the outboard spring is soft, and then kggi is where the inboard spring is soft. So these 4 stiffness matrices are exported from Nastran using the DMAP alter statements, and then imported into ZAERO via the assign matrix executive control commands. So our nominal KGG matrix is named nominal KGG. Our in-out KGG matrix is named KGGIO. Our inboard KGG matrix is named KGGI, and the outboard KGG matrix is named KGGO. And then also we import the nominal mass matrix, which is named NOMMGG. So we'll use the fictitious mass modes to generate a coherent set of mode shapes. So we have 2 large masses added to the rotation 1 degree of freedom of grid points 5002 and 5004 using the CONM2 bulk data cards of Nastran. And the purpose of the large mass at the rotation 1 degree of freedom of grid point 5002 is to trigger a nearly rigid body rotation mode shape of the inboard wing section about the inboard hinge, and the large mass at grid point 5004 triggers a nearly rigid body rotation mode shape of the outboard wing section about the outboard hinge. And this set of fictitious mass modes, which are defined as capital Phi FM, are imported into ZAERO via the assign FEM executive control command here. And the mode shape matrix in ZAERO is stored on the runtime database in a matrix entity called SPhi. Now these are the splined mode shapes on the aerodynamic model. The fictitious mass modes are splined to the aerodynamic model using the infinite plate spline method. The first 2 modes are nearly rigid body rotation modes about the inboard and outboard hinge lines due to the fictitious masses. And the rest of the modes are elastic modes. And during a nonlinear response simulation, the first mode and second mode can represent the physical deformation when theta is within delta in and theta out is within delta out, whereas when theta is greater than delta, the physical deformation can be represented by the elastic modes. Thus, the fictitious mass modes can be superimposed to accurately represent the physical deformation in the entire nonlinear response domain. So our mode 1, it's kind of hard to see, but there is motion, rigid body motion about this hinge line. For mode 2, we have rigid body motion about both hinge lines. And then we have our elastic modes, mode 3, mode 4, mode 5, and mode 6. Next, we'll look at the generalized mass and stiffness matrices. So once the fictitious mass modes are obtained, they are used to compute the generalized mass and stiffness matrices of the 4 sublinear structures by these equations. So note that we always use our fictitious mass mode shapes, and then we have our mass matrix here, and then we have our 4 different stiffness matrices here. Now these matrix operations are accomplished in ZAERO using the alter bulk data cards. So using the alter card, we'll go through the mass here as an example. We start out with the nominal MGG, which remember was imported into ZAERO using the assign matrix command. We post multiply that by SV to get SMGH, and then we pre-multiply SMGH by the transpose of SV to get SMHH. Meanwhile, if we look at the KGGIO, if we take KGGIO post multiplied by SV, that gives us SKGHIO. And then if we pre-multiply SKGHIO by the transpose of SV, that gives us our SKHHIO. And next we'll do a comparison of natural frequencies computed by the fictitious mass method and the direct methods for the 4 sublinear structures. So in order to verify the fictitious mass modes do not change the characteristics of the 4 sublinear structures, the natural frequencies of each sublinear structure is computed in Nastran by these equations. In ZAERO by these equations. So now omega normal, omega in, omega out, and omega in out are the natural frequencies of the 4 sublinear structures. And then CFM are the modal coordinates of the fictitious mass modes. So if we look at this table, when we compare the direct method and the fictitious mass method, we get very similar natural frequencies, which is what we want. So this indicates that using the one set of fictitious mass modes can represent each of the 4 regions accurately. Next, we'll look at the offset moments that are required to create the piecewise continuous torque theta diagram. The nonlinear structures of the 4 sublinear systems are represented by their respective stiffness matrices. Now the corresponding torque theta diagram obtained by strictly integrating torque equals the integral of k times d theta would have 2 discontinuities of torque at theta plus or minus delta, which is incorrect. So you obtain this torque theta diagram if you do not include the offset moments. But by applying the offset moments shown here, so we have this k1 minus k naught times delta, this term, we then end up with this piecewise continuous torque theta diagram. So we need to apply these offset moments. And that's done here. Now because there are 2 bilinear stiffnesses of the folding wing, there are 8 total offset moments to be specified for their corresponding expressions. So for the first one, we have theta in is greater than delta in and theta out is greater than delta out. So that's given by this equation, and then each of the 8 cases is specified here. Now delta 1 is a vector of length 2478, where 2478 is the G-set degrees of freedom of the structure model containing all zeros except a value of delta in at row position 2464. So this row position 2464 corresponds to the rotation 1 degree of freedom of grid 5002. Delta 2 is similar to delta 1 except it's for the delta out row position. And then delta 1 P2 is delta 1 plus delta 2, and delta 1 M2 is delta 1 minus delta 2. Next, we need to define the 8 offset moments via the alter bulk data cards. Now, if we assume delta in equals delta out equals 0.1 degrees, then the delta 1, delta 2, delta 1 P2, and delta 1 M2 can be specified by the DMI and DMIS bulk data cards as shown here. So this is selecting the correct row position, and then these is specifying the values of those particular row positions. And the 8 offset moments can be generated by ZAERO internally using the alter bulk data cards here. So our nominal KGG times del1 P2 gives us our KTP11, and then we pre-multiply our KGG-IO times del1 P2 gives us KTP12. Then if we subtract the 2, that gives us KTP1. And then SV times KTP1 is our positive offset, and then minus SV times KTP1 is our negative offset. The remaining offset moments can similarly be defined using alter bulk data cards. Next, we will have the equations of motion of the sublinear aeroelastic systems. Now, the nonlinear equations of motion of the folding wing with 2 bilinear stiffnesses can be subdivided into 9 sublinear aeroelastic systems, where each sublinear aeroelastic system has its respective generalized stiffness matrix and offset moment. And the equations of motion of these 9 sublinear aeroelastic systems can be specified using the nonlinear system matrix bulk data card, as shown here. Our sublinear system 1 is where theta in is greater than delta in and theta out is greater than delta out. So in this case, we need to apply our offset, and then we have our nominal KHH matrix. So this base here refers to the fact that we use our nominal mass, damping, and stiffness matrix, and we're just applying the positive offset moment. When theta is less than delta, negative delta in, theta out is less than negative delta out, then we use the negative offset. Moving on to within the soft regions, if theta out is inside the soft region, then we have our stiffness matrix is modified to be SKHHO when and then this is when, so theta in is greater than delta in, we use the positive offset. When theta in is less than negative delta in, we use the negative offset. Next, we have theta in is within the soft region for these two cases. So our stiffness matrix is SKHHI. And then lastly, when we have both theta in within plus or minus delta in, theta out is within plus or minus delta out, we have no offset matrix, and then our stiffness matrix is SKHHIO. Now SCHH is the generalized damping matrix automatically computed by ZAERO, and the damping coefficients are specified by the tab DMP1 bulk data card. For this case, a 1% structural damping is specified. And then FG in these equations is the generalized external excitation forces. In this case, it's due to a 1 minus cosine discrete gust profile specified by the dGust bulk data card. So next, the ZAERO nonlinear flutter module will construct the state space equations. So the frequency domain generalized aerodynamic force matrix Q of IK is transformed into the time domain using the rational function approximation technique. And after the time domain rational function approximation of the generalized aerodynamic forces is obtained, the 9 sublinear equations of motion are recast into 9 state space equations, shown here. X dot is AX plus BU plus C. And our X is Kc dot, and XA, where XA are the aerodynamic lag roots. Now the nonlinear flutter module solves the nonlinear aeroelastic responses based on the nonlinear parameters that are defined by theta in and theta out. At each time step, the value of theta in and theta out are first computed to find their corresponding sublinear aeroelastic system. Then, that state space equation of the corresponding sublinear aeroelastic system is used to solve for x for the next time step. So this is a description of our input file. The flight condition is at Mach 0.8. altitude is 25,000 feet, specified by the Flutter, MK-AeroZ, and Fix MATM bulk data cards. And based on the built-in atmosphere table, the free stream velocity at this flight condition is 812.8 feet per second. The MinStat bulk data card transforms the frequency domain generalized aerodynamic forces to the time domain using the minimum state method with 8 aerodynamic lag roots. These 8 aerodynamic lags are specified by the aero lag bulk data card with ID equals 81. And in order to excite the aeroelastic system, a 1 minus cosine gust is introduced using a d.gust bulk data card. The gust reference point is located ahead of the origin of the aerodynamic model by 406 feet. A 30 foot per second gust velocity is specified, which gives a gust angle of attack of 0.03691 radians. So this is the nonlinear flutter bulk data card. So we're referring to the flutter card, the MinStat card. We have our 8 aerodynamic lag roots. Here's our discrete gust. So that defines our excitation. Our MLD time defines a starting time of 0, an ending time of 25 seconds, a time step of 0.001 seconds, so 1000 hertz. And then our output, we're going to reduce the output by a factor of 10, so our output will just be 100 hertz. And then our MLD print here, we're looking at several grid. So we have a grid rotation, and then we have a grid displacement, grid velocity, and grid displacement and grid velocity in the z direction. This is our table of nonlinear system matrices. So this is just this table here. So when theta in is less than 0.00175, we use this row of nonlinear system matrices. When theta in is within the soft region and theta out is within the soft region, you can see we use nonlinear system matrix 109. So as I said earlier, if we're within plus or minus 0.00175 for both theta in and theta out, ZAERO will interpolate among the nonlinear system matrices 109, 109, 109, and 109. So obviously when you interpolate among 4 constants, you just get back that constant. So within that region, we have the constant matrix defined by the nonlinear system matrix card 109. And then because our values here are the same, so we have positive 0.00175 and positive 0.00175, we simply switch to the next one. So we avoid all interpolation. So we're doing a constant switching. However, at this particular value, both nonlinear system matrix 109 and 105 will evaluate our mass, damping, and stiffness matrices will be the same. So we get a piecewise continuous system. So there's no discontinuities. Okay, let's look at the results. So the time domain responses can be output via the MLD print bulk data card. So in this plot, we're looking at the hinge rotation angle of the inboard, and this is the outboard hinge rotation angle. So at this flight condition, you can see it's hit by the gust, and then we start to develop some LCO. So first, the response starts growing, and then it settles into LCO. This plot is now the displacement of the grid 200 versus time. So you can see also we're developing the LCO. This plot gives us a plot of the velocity versus displacement. So you can see that we have this somewhat harmonic motion. And this is, let's see, these two plots are for grid 91. This is for grid 200. Grid 200, you can see we have actual harmonic motion for this grid. In the plot, the velocity versus displacement. Whereas at grid point 91, we have a little more complicated motion. Okay, our next case study will be the 3.0 airfoil with Freeplay, but this time modeled by a closed-loop system. So the 3.0 airfoil with the Freeplay sample case can be simulated by a closed-loop system to remove the hinge stiffness rather than modeling two different stiffness matrices. So once again, minus h is the vertical displacement, alpha is the pitch angle of the wing, and beta is the relative deflection angle between the wing and the control surface. Now, rather than modeling the nonlinear stiffness in the stiffness matrix, the nonlinear stiffness at the hinge is modeled by a nonlinear gain in a feedback control system. In the nonlinear feedback control approach, it can be shown that the control force can remove the stiffness of the rotational spring between the wing and the flap, creating a closed-loop system that is equivalent to the structure in the Freeplay region. So first, the nominal structure is used as the baseline structure. Then two sensors are used in the plant model to measure the relative rotational angle between the flap and the wing, and two grid point forces acting at the grid points on the wing and the flap with a magnitude of minus 3.9 and positive 3.9 are defined. Now note that the magnitude 3.9 is equal to the rotational spring stiffness of the nominal structure model. And then finally, the system is closed by a 2-input, 1-output MIMO system, y equals d times u. And the inputs of the MIMO controller are the two sensor measurements, and the output is the command to the grid point forces. Now by defining d1 as 1 and d2 as minus 1, it can be shown that the closed loop system can disconnect the rotational spring through the feedback control system. So we'll review the equations of motion here. By applying a grid point force vector to the nominal structure, the equation of motion of the aeroelastic system now is given by this equation, where c are the modal coordinates, which are minus h, alpha, and beta. These are the generalized coordinates. Delta g is the command from the controller to the grid point force vector, and fg is the grid point force vector defined in the g set, where k beta at 3.9 is the stiffness of the rotational spring. So our fg is given by this vector, and then phi transpose is given here, which is the mode shape matrix. Now the output equation of the two sensors is given by this equation. So y1 is the first sensor output, which measures the total deflection angle of the control surface due to alpha and beta, and y2 is the second sensor output to measure the pitch angle alpha. Now the closed loop system is constructed by a zero-order MIMO controller given by these equations. So we take the output of y1 and then subtract y2, which gives us beta. And then finally, the equation of motion of the closed loop system, once we simplify these equations, is now given here. So we can see that our closed loop feedback is just k beta times beta. So when we subtract, or we move this term to the left-hand side, then that means we subtract out the k beta times beta term from the stiffness matrix, which leaves the Freeplay model. So this above derivation proves that the closed loop system is equivalent to the open loop aeroelastic system with the rotational spring removed from the structure model. Now, however, if we define the grid point force Fg as the zero vector, then the equation of motion of the closed loop system leads to the open loop aeroelastic system with the rotational spring being left intact. So now we'll set up the closed loop system in the ZAERO input deck. So the ASE controller bulk data card represented here in the diagram refers to the SenSet bulk data card with ID 1100 over here that lists two sensors defined by three ASE sensor bulk data cards with ID 1 and 2 as shown here. And once again, we have both definitions, the old style ASE sensor definition, and then we have the new style ASE sensor 1 definition. I recommend using the new style ASE sensor 1 definition because it's easier to read. So we can see that the first sensor is the rotational displacement, the y rotational displacement about grid point 2. The second sensor is the y rotation displacement about grid point 1. So the first sensor measures the pitch angle at the flap, which is alpha plus beta, which is component 5 of the grid point ID2, and the second sensor measures the pitch angle of the wing alpha of grid point 1. Thus, the difference between the two sensor measurements is the relative rotation angle between the wing and the flap, which is just beta. Next, we have the TF set bulk data card, referred to by the ASE controller bulk data card, that lists a 2-input, 2-output C-junct bulk data card, which is shown here. The reason we have 2 outputs is one of the outputs will be used in the closed loop controller, and the second output will be our EXT out, our external output, which will be used by the nonlinear Flutter module. The 2 inputs of the C-junct are the outputs of the ASE sensor bulk data cards. The first output of the C-junct card is the difference between the two sensor measurements, which is beta. The second output is identical to the first output, but it will be used for the external output. And the external output is referred to by the ASE controller card. The external output has no effect on the stability of the closed loop system and is used as the nonlinear parameter in the nonlinear Flutter analysis. Continuing, the ASE controller card refers to a surf set card and a grid F set card. Now the surf set card refers to the AE surf Z bulk data card for defining the control surface. This control surface has no effects on the stability of the closed loop system, and it's used in the nonlinear Flutter analysis to excite the system with 1 cycle oscillation. The grid F set bulk data card refers to the grid force card with the label ACT as shown here. Now this grid force bulk data card defines a moment of minus 3.9 applied to the wing. So that's applied at grid with ID 1 at component 5, which is the Y rotation, and then a moment of positive 3.9 applied to the flap. So that's applied to grid with ID 2 and the Y rotation degree of freedom. This is referred to by the CISO TF card down here that defines a 0-order transfer function with unit gain. So our actuator here is just 1. The CNCT set card is referred to by the ASE controller that lists out the 3 fixed connection bulk data cards as shown here. The fixed connection cards connect the 2 ASE sensor cards to the C-junct and then the C-junct back to the actuator, which is the actuator, the CISO TF, which is the actuator for the grid force card. So next we'll look at the results, or validation results here. The ASE stability analysis is performed at an air density of 1.225 and speeds ranging from 1 to 29 meters per second. The Flutter analysis is also performed using the G method for the open loop system of the structure with the rotational spring between the wing and the flap being physically removed from the finite element model. And excellent agreement between these two results is shown below. So our ASC, that's the closed loop analysis. Those are the lines, the solid and the dashed line, and then the G method of the modified structure, the Freeplay structure, are the open symbols. And you can see that the two agree very well in both damping and frequency. And if we come down and look at the Flutter results, mode 1 in the closed loop is 7.04 meters per second, and the G method is also 7.04 meters per second. Frequency is also the same. The Flutter speed of the second mode is also the same, and the frequency is the same. So this validates that the ASC closed loop methodology works to remove the spring stiffness from the nominal structure to give us back the Freeplay structure. This time we will leave the rotational spring intact. So to define the closed loop system for the relative rotation angle between the wing and flap outside the Freeplay angle, it's required to specify a controller that has identical topology to that defined in the previous ASE case, except representing the nominal structure with the rotational spring being intact. So what's going on here is in our nonlinear Flutter analysis, you are allowed to have different closed-loop control systems that are referred to by your different nonlinear system matrices. However, the topology of the control systems must be identical. So what you're doing is just changing factors in the control system. So we have the same grid force and CSO-TF, but now the factor, the force that we're applying with the grid force, we're setting it equal to 0. So when we set the feedback force to 0, then of course it has no effect, even though the closed loop controller is physically present. So the ASE bulk data card refers to the ASE controller that refers to this grid force card with label 0. And the flutter analysis is performed using the G method for the open loop system of the nominal structure. And then again, we have excellent agreement between the two results as shown here. So our flutter results, we get the same flutter speed and flutter frequency. So now we'll move on to define our nonlinear system matrices. So the nonlinear domain of the 3.0 airfoil with Freeplay and the flap can be divided into 3 sublinear domains shown in the figure to the right. So this is our torque theta diagram. We have our Freeplay region when delta is within plus or minus 2.12 degrees, and then we have outside the Freeplay region, specified by regions 1 and 3. So the 3 nonlinear system matrix bulk data cards shown here are used to define the 3 sublinear domains. For regions 1 and 3, we have the offset moments to shift the curve up so that we have piecewise continuous curve here. And then for region 2, we have no offset moment. And also notice that for our mass damping and stiffness matrices, we're just using the base matrix in all 3 cases. Because for the Freeplay region, remember, we're not modifying the stiffness matrix, we're using the closed loop controller to take away the spring stiffness. So the matrix K delta P is the same as before, and K delta M is the same as before as well. And then only one nonlinear parameter is used, the flap rotation angle beta, which is used to describe the nonlinearity of the system, where beta is the difference between the rotational degree of freedom about the y-axis of grid points 1 and 2. An alternative way to define the nonlinear parameter is to use the external output specified by the ext out card, because this external output is directly the measurement of beta. So that's what we will be doing here. So now we'll set up the nonlinear flutter bulk data card. So we have 3 nonlinear flutter bulk data cards to perform the nonlinear flutter analyses for Freeplay angle of plus or minus 2.12 degrees at these 3 different speeds, 6.5 meters per second, 10 meters per second, and 17.5 meters per second. So you can see we have our 3 sublinear regions defined. And this table is the same for all 3 subcases. The only difference between the 3 subcases is we refer to different flutter cards. So we have a flutter 101, 201, 301, and those define the 3 different speeds. And we have 3 MLD print cards with IDs 1, 2, and 3 shown here that are specified to store the transient responses of the those 3 degrees of freedom in the files Freeplay 27, Freeplay 43, and Freeplay 73. Now if we look at the output file of ZAERO, this is the time history we have grid 1, the rotational degree of freedom, grid 2, rotational degree of freedom, and then grid 1, vertical translation. This is for a speed of 6.5 meters per second. Moving on to 10.3 meters per second. This is our output in the output file generated by the MLD print card. And of course, we could also use the MLD print output file to plot this data in MATLAB, for example, to get nicer plots. But you can quickly look at the ASCII art in the output file to get an idea of what's going on. And then this is our highest speed at 17.5 meters per second. Okay, next we'll look at our case study, a folding wing with Freeplay, where the outboard hinge, we have the Freeplay and the outboard hinge at an NZ of 0 Gs. So the aerodynamic model is identical to that of the folding wing with bilinear stiffness in the hinges that has been shown previously, and the structure model is modified from that of the folding wing with bilinear stiffness in the hinges. So the bilinear stiffness in the inboard hinge is removed, and the bilinear stiffness in the outboard hinge is replaced with a Freeplay angle of plus or minus 2 degrees. And the grid point with ID 4444 located at the center line of the model is constrained only at 5 degrees of freedom, and it's the vertical displacement is left to be free, which creates a rigid body plunge mode for the trim analysis. Additionally, a 100 slug mass is added to this grid point to represent the mass of the fuselage, and the fictitious mass at grid point 5002 is removed to eliminate the fictitious mass mode due to the removed bilinear stiffness in the inboard hinge. However, the fictitious mass at the outboard hinge is kept to introduce the fictitious mass due to the Freeplay in the outboard hinge. And once again, we're going to remove the spring stiffness by a closed loop system. So by defining the difference between the rotational degree of freedom about the x-axis at grid point 5004 and at grid point 5003 as the nonlinear parameter, then the nonlinear aeroelastic system of the folding wing with Freeplay in the outboard hinge can be divided into 3 sublinear domains. And because the structure model is the nominal structure, except with fictitious mass at grid point 5004, then to create a structure in the Freeplay range requires removing this spring with the rotational stiffness of 10 to the 5. And the moments M1 and M2 at those 2 degrees of freedom created by the spring are shown here. So canceling M1 and M2 can be achieved using the feedback control approach. So once again, we have 2 sensors at grid points 5004 and 5003 that are connected by the spring, which are defined by the 2 ASC sensor cards. And then a C-junct is used that is referred to by the TF-CET bulk data card to define the 2 input, 2 output MIMO controller, as shown here. So the 2 inputs of the MIMO system are the 2 sensors inputs, and the 2 outputs are denoted as Y1 and Y2. And once again, the outputs Y1 and Y2 are identical. So one of them will be used for our feedback, and the other one will be used as the nonlinear parameter. Now the connection between the MIMO controller and the 2 sensors is achieved by the 2 fixed connection bulk data cards. So we'll remove the spring stiffness by the closed loop system. The first output of the MIMO controller is the input of the 0 order CISO controller that's specified by the CISO TF as shown here. And the connection between the first output of the MIMO controller and the CISO controller is achieved by the fixed connection card. And all of the fixed connection cards are referred to by the CNCT set bulk data card, which is then referred to by the ASE controller bulk data card. And the CISO controller is referred to by the grid force card shown here. This grid force card is listed in the grid F-set card. And so the grid F-set card is here, the grid force card is here. So we're applying this 10 to the 5, or 1 times 10 to the 5 force on the 2 grid points 5004 and 5003. So this 1 times 10 to the 5 is the rotational stiffness of the spring, which connects those 2 grid points. So this grid force card introduces the moment M1 and M2 at grid points 5003 and 5004 to cancel the moments created by the spring. And the second output of this controller is connected to the external output card. And because the output of the external output card is the nonlinear parameter delta, it can be referred to by the nonlinear flutter bulk data card to perform the nonlinear flutter analysis. So this is the interconnection of our bulk data cards. So the feedback controller is constructed by the ASE controller bulk data card shown here that refers to the grid F-set card, refers to the SenSet card, refers to the TF set card, and the CNCT set card. So the interrelationship of these cards for constructing the feedback controller is shown here. So now we'll continue and define the closed loop system with the spring stiffness being left intact. So a similar feedback controller, except for the spring being intact, is specified using a grid force bulk data card with label 0 that has 0 feedback force. The feedback controller for the spring being intact is specified by this ASE controller card. And the interrelationship of the bulk data cards for constructing the feedback controller is similar to our previous ASE controller, except the grid force bulk data card is now this new one with label 0, and we have a new grid F set, which refers to the new grid force card. Now to generate the offset moments for region 1 and 3, a DMI bulk data card is used to create a vector called delta 2. That is the size 2478 is the number of degrees of freedom of the structure, and 2476 is the index in the G set of the rotational degree of freedom about the x-axis at grid point 5004. And the the 0.035 is the Freeplay angle in radians. So the offset moment in regions 1 and 3 are generated by the following alter cards, which are stored in the runtime database matrices P offset 4 and N offset 4, as shown here. KGG is the G-set stiffness matrix, which was imported by the assign matrix executive control command, and SV is the mode shape matrix, which was imported by the assign FEM executive control command. Our remaining bulk data cards in this analysis, the fictitious mass of 10 to the 5 slugs defined by the conm2 card is removed by a conm list bulk data card that is referred to by the flutter card. So our fictitious mass mode shapes in the imported by the assign FEM card have that fictitious mass in them, so we need to remove that fictitious mass in ZAERO using this conm2 card. So the flutter card is refers to the MK-AeroZ card, which refers to a fixed MATM card to specify the flight condition at Mach 0.8 and an altitude of 29,000 feet. Now the frequency domain, generalized aerodynamic forces, are transformed to the time domain using the minimum state method with 8 aerodynamic lags by these bulk data cards, and we have the recommended constraints here using the AP const card. Now to excite the nonlinear aeroelastic system, a 1 minus cosine discrete gust with a gust velocity of minus 60 feet per second is specified by the dgust bulk data card as shown here. And in our comments here we have our calculations of how we calculate the WGV and the gust velocity. Now the total simulation time of 25 seconds with a time step of 0.001 seconds are specified in the MLD time bulk data card shown here. And finally, the time histories of the results are output using the MLD print bulk data card to store the results on the output file untrim.xls. Now this is an ASCII file. It's just named .xls so that when you click on it, it can open in Excel and Excel can parse the data. But you can use any ASCII file editor to view the contents of this, or you could import this data into MATLAB as well. And finally, a nonlinear Flutter bulk data card with ID 1100 is specified to perform the nonlinear Flutter analysis. Now the entry states equals 0 specified, so no trim loads are applied, so NZ is 0 Gs. And then 101, 111, and 100 are the 3 identification numbers of the nonlinear system matrix bulk data cards as shown here. And once again, our mass, damping, and stiffness matrices are all the nominal matrices for all cases. We have our negative and positive offsets shown here, and then we have our 2 different ASE control systems referred to here. So the controller is what removes the spring stiffness. And this is the interrelationship of the bulk data cards of the nonlinear Flutter card. So the nonlinear Flutter card is shown here which refers to the 3 nonlinear system matrix cards. Meanwhile, it refers to the flutter card, the min-stack card, the dgust card, the external output, and our MLD print and MLD time. Now if we run the analysis and look at our outputs, the results are stored on the file untrim.xls, which shows that the Freeplay with an angle of plus or minus 2 degrees in the outboard hinge can lead to LCO when NZ is 0 Gs. So this is our delta 1 rotation of the grid 5004, and this is delta 2 rotation of grid 5003. This is our acceleration at the wing leading edge and the acceleration at the wing trailing edge, and then this is our nonlinear parameter delta, where the dashed line here represents the Freeplay angle. So you can see that after the gust, it takes about 5 seconds for the LCO to fully develop. And we can look at the animation here. This was animated using the plot time bulk data card for visualization purposes, and we use TechPlot to visualize this animation. Next, we'll look at the same case study, except now at a 1G load factor. So the trim analysis is used to determine the required angle of attack for an NZ of 1G. So the purpose of the trim analysis is to determine the required angle of attack for 1G cruise. This trim analysis at Mach 0.8 and dynamic pressure 295.1 PSF is specified by the trim bulk data card with ID 100. The trim solution is used as the initial condition for the nonlinear flutter analysis. So here we've got our mass of the structure, and then our inertia terms. Now, since there is only one rigid body plunge mode, this is a 1 degree of freedom trim analysis. So NZ is 1, where G is 32.2 feet per second. Therefore, the trim analysis is to determine the required angle of attack to generate the lift for sustaining the weight of the aircraft. And we have 2 trim variables specified by the trim var cards. So trim var 1 is thick cam, which is set to 1. This is the mean flow. And then trim var 2 is alpha, which is set to free. So this is the unknown angle of attack, which the trim module will solve. And the trim bulk data card refers to a set 1 card that lists the identification numbers of the trim function cards as shown here. So we're going to be able to monitor the hinge moment, the shear, and the rotation of grid points 5003 and 5004. The trim solution shows that the required angle of attack for 1G cruise is 0.99498 degrees, and the hinge moment on the outboard hinge is approximately 1,000 foot-pounds, and the shear on the outboard hinge is approximately 4,000 pounds. The rotation at grid point 5003 is 0.237 degrees, and the rotation of grid point 5004 is 0.9 degrees. So next we'll set up the nonlinear flutter analysis. So the nonlinear flutter analysis for the folding wing with Freeplay at NZ of 1G is specified in this nonlinear flutter bulk data card as shown here. The nonlinear flutter bulk data card is nearly identical to our previous test case, except the entry states equals 55. 5 refers to the MLD stack card, which then refers to the MLD trim card, which specifies the initial trim condition. So our load factor of 1 is specified. So G is 32.2, NZ is 1, and our alpha is the 0.99498 degrees. And then the modal coordinates of the 30 modes obtained by the trim solution are copied and pasted from the trim output to our nonlinear flutter input shown here. And the MLD print card with ID 71 is used to store the time histories onto the file trim.xls. So now if we run the analysis and look at the results, we can see that the rotation at grid 5004, which is delta 1, is shown here, Grid 5003, which is delta 2, is shown here. This is the acceleration at the wing leading edge, acceleration at the wing trailing edge, and our nonlinear parameter delta. So you can see when the gust hits the aircraft, our nonlinear parameter delta travels through the free play region and then stays outside the free play region after the gust stops. So the nonlinear parameter initially reaches a minimum value of minus 3.5 degrees due to the downward gust, but it rapidly approaches a steady state value of 3.85 degrees, which is outside the free play angle of plus or minus 2 degrees. So this is the reason that the LCO is suppressed due to the trim loads. And if we look at our flutter mode animation, you can see this from the plot time card. And it's not a flutter mode, it's just the animation of the nonlinear flutter analysis. So we can see that the aircraft travels through the gust, there's a response, and then after the gust hits, everything settles back down, as we saw from the time history traces on the previous slide. So our next case study will look at the folding wing with the wingtip store and the free play at the outboard hinge at NZ of 1G. So in our previous section, we saw that the LCO is suppressed, but now we're going to investigate what happens if we add a wingtip store outboard of the outboard hinge, which has the free play. So the purpose of the study is to investigate the impact of a wingtip store mass on the LCO characteristics of the folding wing with the free play. The wingtip store is not modeled aerodynamically, and a mass of 3 slugs is added to the wingtip to represent the store mass. Now at the 1G trim condition, the inertial loads from the wingtip store mass may reduce the hinge moment about the outboard hinge line. And the reduced hinge moment also may induce LCO even under the 1G trim loads. Now because the structure mass is increased due to the added wingtip store mass, the trim solution needs to be recomputed. And the trim solution shows that the hinge moment indeed is reduced. So our angle of attack with the store mass decreases, and the hinge moment, as you can see, also decreases from 1,000 foot-pounds to 640 foot-pounds. And the nonlinear flutter bulk data card is identical to that of the previous case, except now the angle of attack is changed to the 0.95838 degrees, and the DMI card specifying our static aeroelastic solution has been updated as shown here. So now we'll run the nonlinear flutter analysis and look at the results. Unlike the nonlinear flutter analysis without the wingtip store that shows suppression of LCO, the present analysis shows that even under trim loads, LCO still occurs, and this is due to the reduced hinge moment by the inertial loads from the wingtip store. So this is delta 1. You can see after the gust hits, then we start developing LCO, and it takes about 15 to 20 seconds to reach a steady state LCO condition. This is our delta 2. This is the acceleration at the wing leading edge and acceleration at the wing trailing edge, and then finally our nonlinear parameter delta. So after the gust, you can see that it's not the hinge moment is small enough that it's not enough to suppress the LCO. So after the gust hits, the system is excited, and because of the free play, then develops into LCO. And once again, if we look at the animation, you can see that the gust hits the aircraft to excite the system, and then LCO develops.